Hi everyone, my name is Chris Simpson. I work for the University of Manchester, for Withers, but I'm actually based down in near Didcot, the Diamond Light Source. So today I'm going to talk about damage evolution in freeze-cast composites, so freeze-cast metal matrix composites. And so, kind of to take a little bit of a step back, why would I want to look at these freeze-cast composites, these metal matrix composites? And that essentially comes back to the idea of these hierarchical materials. And so that's materials that are ordered or structured on multiple length scales and toughened over multiple length scales. And that's something that's often found in natural materials. So typical examples include shell, horn, and cuticles, so kind of the exoskeleton of crustaceans, for example. And so there's a nice example here by Ra. Basically, you can see there that you've got this in the bottom right, the multi-layered cuticle, and then as you go as you zoom in, you see that those layers are offset from one another. And then moving in further, you can just about see there that it's actually a honeycomb structure, which in itself is made up of fine fibres, and so you end up with a material that is both strong and tough and has kind of a complex craft development. And what that's really led to is this idea of biomimetic materials, so man-made materials that try and emulate some of this kind of hierarchical structure, and that's what I'm interested in, really. So interested in looking at the crack initiation and development in this type of material, or this very, very heterogeneous material. And I guess a little caveat before I start is that this is, compared to a lot of the work that I've seen today, and yesterday as well, this is in its very early stages, so I'm obviously interested to see where people think that we should take this work and any comments that they might have. So in terms of in terms of that hierarchical structure, one way of producing it is through freeze casting, which is where you form a kind of second phase scaffold via segregation, and more specifically you suspend second phase particles in a solvent, generally water or water with some kind of additives, and then directionally solidify that before removing the solvent via sublimation. So kind of a direct transformation from solid to gas, before sintering it to get the kind of final densification. And what's really interesting and quite cool about this type of material is, or process, is that you can vary that morphology quite extensively by changing things like the solvent supersaturation or freeze temperature, for example. And there's a very nice paper by Sylvain Deville where he looks at the different morphologies that you can get. So that's well worth a look. So what are we looking at? It's an aluminium alumina composite, a multi-domain MMC, where domains are regions in which the lamella are orientated in alignment with one another, and in this case those domains are, say, 1 to 3 millimeters in size. And what we've done actually is take that preform, apply a copper layer to it before squeeze casting in aluminium. And so for the testing that we're going to explore that we've actually done, we just looked, like I said, because this is quite early on, just looking at a single domain and what's happening in a single domain, and then obviously as time progresses and as the project progresses, we'll look at multi-domain samples. But so single domain samples orientated at 45 degrees, like so. Okay, so this experimental work is in many ways building on some work done by Roy and Wanner, where they looked at the domain level anisotropy in those single domain samples, and they said that you can kind of fairly well describe their strength via the energy-based Tsai-Hill criterion, with the strength being minimized at around 45 degrees due to yielding in the kind of soft metal matrix. They went on from that to looking 2D, so using SEM images at the damage progression under compression. And so part of what I'm doing and what I want to do is, well, it's kind of building up, because is 2D really sufficient when you've got this complex crack development? Do you perhaps need to look in 3 dimensions? And so that's precisely what we're starting to do, is using some of the facilities at the Henry Moseley, the Manchester X-ray imaging facility. So this X-Radia Versa 520, this time we've got a voxel size of the images that, or the volumes that we're producing, of about 2 microns, and then doing an ex situ series of compressive loading steps from 0 to 270 megapascals. So first thing first, the unloaded sample. So we've done a CT scan before we've done that first load step. There's a couple of things that you can see here. So on the top right, you've got a 2D virtual slice, so that's a projection through the volume. And you can see you've got the darker ceramic lamellae and then the brighter metal matrix. And more than that, I've kind of enhanced the contrast here, but actually there's a limited attenuation contrast, a limited number of grey scales between the dark and the dark and light phases. And what that means is it's not really practical to segment that structure automatically at the very least. So if you had a lot of time on your hands, then you could probably segment it manually, but that's something that you wouldn't really ever want to do. But obviously we can segment the cracking, we can segment the porosity, which kind of nicely brings me on to the next point, which is there is obviously quite a lot of damage there. Considering we haven't done any loading yet, there's a significant amount of damage. And that's obviously not what we would ideally want, but there you go. So we've got cracks that are running from that top left to bottom right corner, and those cracks are running along the metal ceramic interface. And actually going back to some of the work by Rowan White, what we can see is that when we've applied the CU coating to the preform, instead of kind of nicely bonding and impregnating into the ceramic and into the metal, it's actually oxidizing and weakening that interface, which is obviously a bit of a problem. But there's still interesting information that we can get from this, but it's important that we only look at damage that's forming separately, so that's initiating and propagating away from that main crack. So that's exactly what we've done. And so again, this is 2D virtual slices projections through our volume, and we've done those loading steps, and what you can see is that at different loads here, but at 170, 175 megapascals, it's very difficult to see, I know, but there's a high magnification images in the next slides, but you're forming damage along the interface of the metal and ceramic, and also transverse to the ceramic lamellae. And basically we can ascribe that to an elastic-plastic mismatch. So this 170 megapascals is approximately around where you start to get yielding in the sample. And that yielding is going to cause 2 things. Firstly, you'll get shear at the interface, and also you'll get a tensile load along that ceramic lamellae. And so essentially you've got one type of damage and one mode 2 damage mode. And then from these 2D virtual slices, it doesn't look as though those are connected, but obviously it's very difficult to tell the interconnectivity in these different cracks. And so that's precisely why you need the 3D method. Okay, and so unsurprisingly, as you increase the load, you get extension of those cracks and increase in the number density of the cracking. And then actual final failure at 300 megapascals. So we loaded it to 300 or 310 megapascals, but as we unloaded it, the whole thing failed, so there's no images of that load. It's also worth mentioning that cracks are beginning to propagate into the metal matrix at the highest loads. The problem is they're quite difficult to resolve, and I haven't looked at those yet, but that's obviously still something of interest as well. Okay, so like I say, you've got those two different types of crack, and what's interesting is to see what is the interconnectivity between them. Is one initiating the other, or what is exactly happening there? So, further to that point, you can see the intralamellar cracking. It's very, very difficult to see on this image there, but you have got cracks forming across the lamella, and those cracks are essentially periodic, periodically forming to relieve the stress that's caused by that elastic-plastic mismatch. But the cracks are long and thin, and essentially constrained by the width of the ceramic lamella. And that's important because these cracks aren't initiating at the metal-ceramic interface and then propagating across the lamellae. This is definitely a distinct cracking mechanism. And then as you increase the load, you can see that those intralamellar cracks are coalescing as well. So like I said, there was periodic cracks which are coalescing. And they're not branching, essentially. That's the order in which the process is carrying. So these cracks are forming and then at later stages coalescing. And the reason I've only looked at those, or shown these two lower loads, is that at higher loads, everything gets a lot more complicated because there is much more interconnectivity then, and it's difficult to distinguish between cause and effect. Okay, and then just the final thing is the interfacial cracking. And obviously, these cracks, like I said before, this is a mode 2 type of crack formation. These are obviously different. These are much broader, and like I say, are just simply running along the metal ceramic interface in mode 2. Again, not initiating from cracks in the ceramic lamellae. Again, this is two modes of failure that are occurring simultaneously. So, to conclude, dominant failure mechanism was one of cracking or damage at the metal ceramic interface, but also we're getting additional cracks across the ceramic lamella, and that's due to, or both of those are due to elastic-plastic mismatch, but this is all being exacerbated, or the cracking is being exacerbated by a weakened Cu interface, or copper oxide interface. And then moving forward, that 3D computed tomography is a useful tool for this type of work, especially when I start to look at slightly more complex situations in which we've got multi-domain samples, and also I want to develop this, look at samples that haven't got that Cu coating, and do in situ testing. Thank you.